We'll be discussing about the buckling analysis of a laminated composite cylindrical shell. So, what is buckling? Buckling is the failure or the deformation that is caused by an axial compressive load, which acts on a beam or a column, and this load exceeds a particular critical value. So this critical value is given by the Euler's equation for buckling. So PCR is the critical force, and it depends on the Young's modulus of the material. It also depends on the dimensions of the beam or column, and also depends on how the column is jointed at both ends. So you can have pin joint or fixed joint, and depending on that your equivalent length changes, and that is factored in by k, that is the coefficient. And once we know the critical load, we can calculate the critical stress. The critical stress is the critical force by area, and we get this equation over here where le is the effective length, and r is the radius of gyration. So le by r gives the slenderness ratio. So why FEA? So using the Euler's formula, we're able to accurately calculate what the critical buckling load is. But when it comes to composite laminated columns, we have multiple materials, which makes the calculation very complex due to the anisotropic nature and the heterogeneity in the material. So what we do is we use FEA that is able to make these complex calculations and uh, factor in the material behavior and the boundary conditions, and provide us with more accurate results as compared to the analytical method.
So now we'll be modeling the column and the end plate in SolidWorks. So first open part, go to the top one, sketch, draw center. Once that is done, draw a line parallel to it and extend it in this manner. Once this is done, we will be dimensioning it. So make sure you're in MMGS. So smart dimension. Give this distance is 100 mm. Then give this as 5. This also is 5. Give the thickness as 3. This length is 20. This is also 20. Finally, the total length. Give it as 385. Now you can exit sketch and select and revolve it. So you have your cylinder. So you can go ahead and save this. Save it as part 1. So now you can close it. Open part again. So now we have to design the end plate. So go to top plate and draw a circle. Make sure you're in MMGS and dimension the circle. Give a dia of 240. Once this is done, you can extrude boss of 20 mm. Go ahead and save this as part 2. Once this is done, we can create an assembly. So go to assembly, then insert components, insert part 1 and part 2. Now what you can do is go to make, select this surface and select this surface. Give it as concentric, click OK. Then select this surface and this surface and give it as coincident and click OK. So once this is done, your assembly is ready.
This is Samat Deeparshi, and I'm going to cover the ANSYS part of this. So firstly, to do buckling analysis, we have to first do the static structure analysis to apply the boundary conditions and loading. So before we begin that, we have to add engineering data. We have already done this once. We'll just go through it again. We can go and add composite materials. And in composite material I have added epoxy carbon. As you can see, it's added epoxy carbon with 230 GPa of elastic modulus. And in uh, in Granta design materials, I have added aluminum 6061 alloy. It's added. These are the two metals that we require. Right, so we have aluminum 6061 and epoxy carbon. Once the material is added, I will click on geometry. I will so we have imported the geometry, which is called as assembly 3. This is an added. No extra modification is done in space clay design modeler. So after that, we'll open the model. Right, so this is our model. We'll go to geometry. We have this revolve one component, and I have, as you can see, I have added epoxy carbon. This is the end plate 1, and I have added aluminum alloy. And in end plate 2 also, I have added aluminum alloy. After adding the materials, the next point is to connections. Yes, contacts. These are all the contacts that are added are all fixed contact. Right, so after that, we go to static structural, and I have applied a fixed support on this face, on the bottom face. So it's like this material is a pressure vessel or a shell which is actually inside the water, and we are adding hydrostatic loading, and then we'll analyze at what pressure value this will buckle. So first pressure I have added on all the side faces, on all the circular revolved faces, and I have pressure as 0.1 megapascal, 0.1 megapascal, because this is the atmospheric pressure, 1 bar. I will order all the pressure, and pressure 2 is all clear on the top, so all pressures will act normal to the surface. So this pressure is acting on the top face. After that, we'll go to mesh. In mesh, I have added body sizing as 10 mm. It could be below this also, but in the student license of ANSYS, the number of elements are restricted, and so if I added 5 mm or something as a mesh size, they do not solve the problem. I have added body sizing on the entire body, and I have added face meshing on this face, because this is a critical region, and here I want the mesh to be very precise. As you can see, this is how the mesh has been turned out. It's pretty decent mesh. Element quality is average. Aspect ratio average is nice, but we have certain elements in this part uh, which are very skewed, so that can also be changed. But again, to change that, that would require a very high computational power, which this uh, software in student version will not allow. And yes, the mesh can be refined more, but to keep the analysis simple and doable, we will not touch it. This part of the mesh is very good, and we'll continue with that. And from solution we will solve it, and then after solving it we will get the total deformation like this. So this is the static deformation. So without buckling, if you only consider the material to be like this, as you can see, the pressure is compressing it radially inwards. So this is how it will be. So once this is done, we will come out to workbench, and inside the workbench, in the solution part, we will transfer data to new, and this will be eigenvalue buckling. Once we do that, we will get one more block like this. And again, the engineering data is same, geometry model, everything is same. So again, when we go to the ANSYS mechanical part, we have come here, and pre-stress condition is added. Analysis setting, I want maximum number of modes to be 5. This is it. Only this condition is required, and once we solve this, it will take a little long time to solve, but once it is solved, we'll get the load multipliers. So we have to multiply. So our initial load was 0.1, and when we multiply 0. You should multiply that pressure with 6.48, so that will come around 0.6. So at that value of pressure, this thin vessel is going to buckle. And then as you can see, the two values are very close, because once it's happening along the x-axis, once it's happening on the y-axis, so in both axes it will happen. So when we take ei, once it will take value as along x-axis, and once it will take value along y-axis, so we'll get close values like this. So once we see, this is how it will buckle. This is how the pressure vessels do actually buckle like this. We have maximum deformation of 1 mm, which is significant considering the vessel is only 300 or 400 mm in length. So it will buckle like this. This is the second mode. This is the third mode. This is the fourth mode. And this is the fifth mode. So yeah, this is it. Thank you.